groundwater. All right. So for us to understand groundwater, we'd have to take cognizance of the water cycle. We have to take cognizance of the water cycle. So with regards to the water cycle, we could think of evaporation, transpiration, and ultimately this form clouds, and the clouds, when they get heavy, we are going to have precipitation. And this precipitation could come in the form of rain or snow or hail. Hail is just like ice rain, right? Ice rain. Rain or snow or hail. Rain or snow or hail. All right. And when this rain falls, we are going to have infiltration and percolation of the water through the surface of the soil into beneath to the subsurface. All right. And then ultimately it ends up in porous rocks called groundwater. And then this groundwater can now flow into rivers or lakes and what have you, or we could dig a well and intercept this groundwater. Great. So what is groundwater? Groundwater is water that exists in the pore spaces and fractures in rock and sediment beneath the earth's surface. Groundwater is water that exists in the pore spaces and fractures in rock and sediment beneath the earth's surface. So groundwater is what you would have typically called underground water. We do not call rivers and streams groundwater. Those are surface water bodies, surface water. And we do not use the term underground water, but rather we say groundwater. All right. So groundwater is water that exists in the pore spaces and fractures in rock and sediment beneath the earth's surface. And it originates as rainfall or snow, and then it moves through the soil into the groundwater system, where it eventually makes its way back to the surface streams, lakes, or oceans. Now, let's look at the distribution of groundwater. It makes up about 1% of the water on the earth, right? So in here, we see groundwater makes about 1% of the water on the earth's surface. And in terms of the distribution of water on the earth's surface, 96.5% of all the water on the planet is in the oceans. 96.5% of all the water on the planet is in the oceans. So we are left with about 3.5%. Out of the 3.5%, we have 1%, which is still salt water, saline water. So saline groundwater and saline lakes. So then we are left with only 2.5%. Out of the 2.5% fresh water available to us on the earth, or on the earth's surface, we only have 30% as groundwater, whereas glaciers and ice caps take almost 70%. And all your streams and rivers and other freshwater sources take 1.3%. So groundwater constitutes 30.1% of 2.5% freshwater. But it is one of the most significant sources of water for us as far as freshwater is concerned. So this is the distribution, and it tells us that there is a need to preserve our water bodies, or there's a need to preserve groundwater. All right, groundwater, because we do not have as much fresh water available to us on this planet like we may think. So Groundwater is the water below the water table, filling entirely all the spaces in a zone called the saturated zone. So water in the subsurface can be divided into two major zones. One is the unsaturated zone, and the other one is the saturated zone. All right. So we have the vadose zone, or the unsaturated zone, and we have the saturated zone. And the thickness of these zones depends on the type of soil, the vegetation, and the rock formation. This brings us to the term subsurface water. So subsurface water includes water in the soil and water that is beneath the water table, called groundwater. So this is what we are talking about. When water or rain falls, this water percolates through the unsaturated zone. And by saturation, it has to do with the amount of pore spaces that are filled with water. So if all the pore spaces are completely filled with water, then we say the zone is saturated. And if the pore spaces are not completely filled, then we say that zone is unsaturated. So we have saturated zone and the unsaturated zone. And the surface that separates the saturated zone from unsaturated zone is called the water table. The water table. All right. So in the zone of saturation, so this is the zone where we have groundwater. Every pore space is completely occupied by water. And we can now harness this water in the form of using boreholes or wells, and then for our domestic or commercial purposes. And when this groundwater also intercepts the land surface, the groundwater at a point will intercept the land surface. That is, in other words, the water table intercepts the surface of the ground. All right. We are going to have a spring. So anytime the water table intercepts the ground surface, we have a spring. All right. So that is the concept of the water table. The water table separates the zone of unsaturation, also known as the zone of aeration or the vadose zone, from the saturated zone or the zone of saturation. So beneath the water table, every pore space is completely filled with water. Groundwater typically follows the topography. When it intercepts the ground surface, or when the water table intercepts the ground surface, we have a spring. And when the spring begins to flow, then we have a stream. And we could also intercept that using a well. The water table fluctuates, the level of the water table fluctuates. So in the dry season, the water table will go down, which means that if your well is not deep enough, you are not going to get water in your well. So the water table goes down, lowers during the dry season, and during the rainy season, the water table rises upwards. All right. So it's important to get this distinction. And rain that falls on the surface seeps down through the soil into a zone called the zone of aeration, or unsaturated zone, where most of the pore spaces are filled with air. And as it penetrates deeper, it eventually enters a zone where all the pore spaces and fractures are filled with water. All right. So when all the pore spaces and fractures are filled with water, that is the saturated zone. And the surface below which all openings in the rock are filled with this water is called the water table. In fact, the water table is everywhere beneath the Earth's surface. Even in the desert regions, it is always present. It's just that it rarely intersects the surface. Right. So we can see that in the dry season, water table is below, and then the stream can even go dry, right? But then in the rainy season, we see the water table rises, and then water will be flowing through your stream. All right. But there are some streams that have water flowing through all the time. So we have the water table. When it intersects the surface, we have a spring, and then this could take the form of a lake, or how do you call it, a swamp, or a stream. And this is an oxbow lake, all right? And this is the a stream and its tributaries, all right? And then a floodplain, which are the zones or areas that get flooded during a flooding event, all right? Groundwater is not stationary. In fact, it is in constant motion. Although it's not going to flow as fast as we would have if we were dealing with, say, a stream, because groundwater has to find a way of passing through the pore spaces of rocks, the particles. It's like weaving its way through these intricate passageways between free space in the rock. So because of this, groundwater is not doesn't move that fast like in a stream, but it is in constant motion. So first, the water moves down due to the pull of gravity, but this water can also move upward because it will flow from higher pressure areas to lower pressure areas. There are two key factors that affect the rate of groundwater flow, and that is porosity and permeability. Porosity and permeability. All right, so porosity has to do with the amount of what? Voids or space that we have in a rock or sediments. That's the porosity. All right. The amount of holes or space we have, that's the porosity. By this explanation, it means that it is possible for a rock or sediment to be porous, but not permeable. It is possible for a rock to be porous, but not permeable, because you can have a lot of holes in the material, but if the holes are not connected, then that material can store water somehow, but it will not be able to transmit the water. All right. It will not be able to transmit the water. All right. So in geology, like we said, groundwater refers to water in beneath the water table. And we do not use the term underground water, but groundwater. So the term is groundwater. What you may think of as underground water is what we call groundwater. All right, that's what you may think of as underground water, but the term is groundwater. All right, so subsurface water, like we said, is classified into two. We have water in the soil and groundwater. Groundwater. All right. So these pore spaces, as we have it here, that's the amount of pore spaces gives us the porosity, right? The amount of pore spaces, empty pore spaces, give us the porosity of the rock or sediment. And then the permeability has to do with the interconnectivity of the holes, all right? The interconnectivity of the holes and the size of the interconnections, because groundwater will have to weave its way through these intricate pore spaces. So the rate of groundwater flow is controlled by porosity, which is the amount of pore spaces in the rock or sediments, and the permeability, which has to do with the interconnectivity of these holes and the size of the interconnections. All right. So we already talked about what porosity is a percentage of the volume of rock that is open space. And this determines the amount of water that the rock can hold. All right. Now, sedimentary rocks, for instance, porosity depends on the size of the grains, the shape of the grains, the degree of sorting, and the degree of cementation. The size of the grains, you understand. The shape of the grains, whether it is circular, it is rounded, it is angular. The degree of sorting. When we say sort something out, it means pick out, arrange it in different sizes. For instance, you are sorting similar things at one side. So when we have well-sorted sediments, it means that all the particles are of the same size. So let's say we have rounded and well-sorted sediments. Then that basically means that we are going to have a lot of space in between them because they are rounded and well-sorted, particles of the same size. They can hold a lot of water. It means porosity increases. All right, so well-rounded coarse-grained sediments usually have higher porosity than fine-grained sediments. So if the sediments are fine, there will be little space between them, and so they will have lower porosity. They will have lower porosity. All right. Now, that is the concept of sorting. What about cementation? Do you remember we talked about this chemical water or acidic rain or water? And we talk about the fact that this carbonic acid, for instance, can dissolve limestones completely. So limestones, we know, are natural cements, and even cement for construction is developed from limestones, right? So if we have these chemical cementations, water passing through with this natural cement and it deposits in between, then we are going to have cementation in between the pore spaces, which means that the pores are closed. And once the pore spaces are closed, then it means basically that we are not going to have any spaces left for water to be able to pass through. So that is cementation. That's a cementation. All right. So this is poorly sorted. So you can see that we have particles of different sizes. So we call this poorly sorted. This is well sorted. So in this well sorted case, we see that we have particles of only one size. But then there's a problem here. We have cementing in between this. So it means that the porosity is going to be low. But this is poorly sorted. So the porosity will also be what? Low here, because particles of different sizes will fit into each other. So low porosity. Now, in igneous and metamorphic rocks, porosity is usually very low. So in all these cases, we have low porosity. Porosity is usually very low because the minerals tend to be intergrown. The only way igneous and metamorphic rocks can have high porosity is where we have a lot of fractures in them. So if we have a lot of fractures in igneous and metamorphic rocks, then it means that porosity can improve and we can store water. All right. We already talked about permeability. It's a measure of the degree to which the pore spaces are interconnected and the interconnectivity of the pore spaces. And a good example of a rock with high porosity and low permeability is a vesicular rock. So high porosity does not mean high permeability because you can have a lot of holes, but if the holes are not connected, there will be no flow. There will be no flow. All right. So pumice like and scoria, these are volcanic rocks with a lot of holes in them, but they are not connected. The holes are not connected. So that is the concept of permeability and porosity. All right. Now, there are certain parts of the Earth where water is entering the groundwater regime or entering the subsurface environment. And there are certain parts also where water is leaving the groundwater regime. So the Earth's surface can be divided into areas where some of the water seeps into the saturated zone and other places where the water leaves the saturated zone. So places where water is entering the saturated zone are called recharge areas. Recharge, like recharging a battery or something, recharge areas. And places where we have water leaving, like in a stream or river or swamp or spring or lake, are called discharge areas. Discharge areas. because in the discharge areas, the water basically leaves the system. All right. In order to understand this concept of recharge and discharge, we have to think about something called the hydraulic gradients. What is hydraulic gradients? Now, imagine we have this box in the subsurface. Think about this experimental setup. And water is passing through here and coming out here. As the water passes through here, the pressure will be high. So the head, we call that the head, the head of the water, head. By head, we mean the energy level of the water, head. All right, head. All right, so the head of the water here is going to be high. As the water moves through the column, it's going to have a reduced pressure because it is weaving its way through these intricate pore spaces. And then we are going to get to this point where the energy level reduces. So this change or drop in head is called water H, change in head, right? So that is like H1 minus H2. So that's basically H1 minus H2. All right. So the H1 minus H2 is the change in head. If we divide that by the length of the column, we get a parameter called hydraulic gradient. And the letter we use to represent hydraulic gradients is the letter I. The letter I. All right, the letter I. So we are talking about motion of water through this medium from point 1 to point 2. And as it moves, there's a drop in the energy level, and that's what we call the change in head. There will be a change in head, H1 minus H2 over L. And that gives us a parameter I called the hydraulic gradient. All right. So the flow velocity V is directly proportional to I. The velocity of flow is dependent on this hydraulic gradient. So it means that we have to introduce a constant of proportionality. Is that not it? So V will be equal to what? K I, where K is the constant of proportionality, also called the coefficient of permeability. The coefficient of permeability. All right. Now, so V is equal to Ki. So the flow velocity is directly proportional to the gradient. The hydraulic gradient is defined as the difference in elevation divided by the distance. So that's the hydraulic gradient. All right. So velocity V is equal to Ki, where I is H2 minus H1 or H1 minus H2 over L. Now, if I multiply both sides by area, if I take into consideration the area, I now have area times velocity, and then KIA, Kotoka International Airport. So area times velocity, this term is Q, all right, and Q is called discharge. Discharge, another word for discharge is the flow rate or the rate of flow. Flow rate or discharge. All right, so Q is equal to KIA, and that is basically what we call the Darcy's law. Darcy's law. All right. So what is Darcy's law? Darcy's law states that there is a linear relationship between flow velocity, V, and hydraulic gradients, I, for any given saturated soil under steady laminar flow conditions. Darcy's law states that there is a linear relationship between flow velocity V and hydraulic gradients I for any given saturated soil under steady laminar flow conditions. So we'll explain laminar flow. So we can have two types of flow. One where the Like when you see a stream, a gentle stream, you see, you can't even perceive that the material is moving or the water is moving, and that is laminar flow, gentle flow. And turbulent flow has to do with irregular motion of water, like when we have a heavy rainfall and you see water gushing through a gutter. All right. So V is proportional to I. It means V is equal to KI. All right. So if the rate of flow Q through cross-sectional area A of the soil mass, then that law can be expressed as V is equal to Q over A is equal to KI. In other words, just remember that Q is equal to what? How do you call it? KIA. That is enough for you. KIA. All right. And the I is the hydraulic gradient, which is what? Change in H over L. Change in H over L. All right. Great. So we already talked about what a spring is. It's an area on the surface of the earth where water table intersects the surface and then the water flows out of the ground. And springs occur when an impermeable rock called an aquiclude intersects a permeable rock that contains groundwater called an aquifer. So what is an aquifer? An aquifer is a permeable rock or sediment that stores, a porous rock, permeable rock that stores water in the subsurface environment. That is an aquifer. So aquifer is not the water. Aquifer is the permeable rock that is storing the water. All right. And when we have an impermeable layer, we call it an aquiclude. Aquiclude. So we have an aquifer. So we have aquiclude. Now, if we just position permeable and impermeable rock together, so here the impermeable clay here is an aquiclude, and the permeable sand here is what? An aquifer. Where these two meet, we have the water coming out naturally, and that is what? A spring. A spring. So when the water table intersects the ground surface, we have a spring coming out. So springs form where the water table is higher than the surface of the ground. Springs form where the water table is higher than the surface of the ground. All right. So an aquiclude can be like a clay layer, and an aquifer like a porous sandstone, or sandstone without cementation. What about a geyser? A geyser is a special type of hot spring. All right, a geyser is a special type of hot spring, and it's a spring characterized by intermittent discharge of water ejected turbulently and accompanied by a vapor phase. So it's like a fountain. A geyser is like a fountain. All right. So we see this ejection, hot ejection of water, and geysers are not common. They are not everywhere. But when we have a geyser, it means that water at a depth of around 2 kilometers is coming into contact with hot rocks. So this is happening near magmatic origin or active magmatic zones. All right. So the boiling of the pressurized water results in the geyser effect we are seeing because it is in close proximity. The water comes into close proximity with an active magma. All right. And when they do occur, they can be tapped for domestic purposes or commercial uses, for heating of homes and all that. So that is a geyser. It's a special type of hot spring. It's a special type of hot spring. Great. So the last thing we want to talk about today is wells. Wells. So what is a well? It's a human-made hole that is dug or drilled deep enough to intersect the water table. And wells are usually used as a source for groundwater. So a well is a man-made hole, all right? It's a man-made hole. It can be mechanized or not. It can be a hand-dug well, or it can be machine-drilled well. All right, so if the well is dug beneath the water table, water will fill the open space to the level of the water table and can be drawn out by a bucket or by pumping. All right. Fracture systems and patch water bodies can often make it difficult to locate the best site for a well. So in order to locate the best site for a well, you need to do geophysical siting. And our departments, we offer that kind of service where you tell us, okay, this is my house, this is my land, I want to drill a borehole. Show me exactly where I can find the most water and tell me the depth of the water table. So we can give you all those parameters and tell you exactly where to drill to find the water by using geophysics. All right, just connecting some equipment and sending some waves down there, some pulses down there. We can, when we intercept water, we can tell you there is water at this depth. And when you drill, you get the water at that depth. If not, you end up hitting a dry hole. It means you're going to pay the drillers, but then you lose your money. And you don't have your well also. All right. So here we have a well, and we can see the fractures here. So there's some water in this well because the fractures are bringing in water. And here we have a dry well because there's literally no fractures, no fracture system. The rock itself is not permeable enough, so basically we are not getting water in this well, although this well is deeper than this well. Over here, this kind of water is the patched aquifer because the water is in a small zone. So you drill your well and get there and think that you hit the water table, but in reality, there's a patched water body. So you needed this well to go deeper into the actual water table. You needed the well to go deeper into the actual water table. All right. You needed the water to go deep into the actual water table for you to get sufficient water. And if not, so you can see in between these patch water tables, we are having a dry well. We are having a dry well right here. So, but if the well were to intersect, go into the main water table, then we were going to have, how do you call it? We're going to have water in our well. All right, we're going to have water in our well. So that's the concepts as far as this wells and patch water bodies and fracturing system and how they could influence how we get water. All right.